In May 1943, three massive German dams stood defiant against British bombing raids. Engineers called them impregnable. Torpedo nets protected their faces. Anti-aircraft guns ringed their perimeters. Conventional bombs had proven useless. Then, in the darkness before dawn on May 17th, Lancaster bombers skimmed just 60 feet above the water, releasing spinning cylinders that bounced across the surface like stones thrown by a child. The dams exploded. Water roared through the Ruhr Valley. The impossible had become reality. The man behind this weapon was not a general or a combat pilot, but a quiet aviation designer named Barnes Wallis, whose obsession with precision had turned a simple schoolboy trick into one of the war's most audacious weapons. Barnes Neville Wallis was born in 1887 in Ripley, Derbyshire, into a family where engineering was dinner conversation and problem-solving was instinct. His father, a doctor, moved the family to London when Barnes was 2. The boy grew up in an era when machines were transforming civilization, when airships floated over cities and steel towers climbed toward the sky. Wallis attended Christ's Hospital School in Horsham, but his family's modest finances forced him to leave at 17. He joined an engineering firm in Blackheath, learning the craft not through university lectures, but through grease-stained drawings and factory floors. In 1913, Wallis joined Vickers to design airships, a field so new that every calculation was an experiment. During World War I, when the government briefly canceled aircraft development, he tried to enlist. He failed the eye test the first time, memorized the chart, and passed the second, but before he could march, the program was reinstated. Wallis returned to designing the future. By the 1920s, he had become one of Britain's leading aeronautical engineers, pioneering geodetic construction, a lattice framework that made aircraft both lighter and stronger. His R-100 airship became the largest in the world. Where others saw metal and fabric, Wallis saw geometry, stress, and efficiency. He believed that every ounce mattered, that every angle could be optimized, that engineering was not art but mathematics made visible. When the Second World War began in 1939, Wallis was already in his 50s, too old for combat but too obsessed with logic to sit idle. He spent evenings studying maps of Germany's industrial heartland, the Ruhr Valley, where factories churned out tanks, munitions, and aircraft. The entire operation depended on water. Massive dams controlled rivers, powered hydroelectric stations, and supplied steel mills. Destroy those dams, Wallis reasoned, and Germany's war machine would grind to a halt. The problem was that no one knew how. The dams were colossal structures, reinforced concrete 140 feet thick at the base, protected by torpedo nets and impossible to approach without being shredded by anti-aircraft fire. RAF Bomber Command had tried. Conventional bombs dropped from high altitude either missed completely or bounced harmlessly off the dam's sloped faces. The Air Ministry dismissed the idea as impractical. Wallis refused to accept that answer. He began calculating. If a bomb could be delivered directly against the dam's face, below the waterline, the pressure wave from the explosion would shatter the masonry from within. But how to get a weapon there? Torpedoes couldn't penetrate the nets. Dropping a bomb from high altitude was too inaccurate. Then Wallis remembered something he had seen as a boy, skipping stones across a pond. What if a bomb could bounce across the water like a stone? If released at the correct speed and altitude, it would skip over the protective nets, strike the dam, and sink against the wall. The idea seemed absurd. Military officials laughed. Bombs were not toys. Water was unpredictable. The variables, speed, altitude, backspin, weight, and trajectory, were too complex to control. Wallis ignored them. He built a small wooden model and began testing it in a wash tub in his garden. His children watched as their father, a respected engineer, spent hours bouncing marbles across bathwater, recording angles and distances in a notebook. Neighbors thought he had gone mad, but the mathematics worked. Wallis discovered that if a cylindrical bomb was spun backward before release, the backspin stabilized its trajectory across the water and, crucially, caused it to cling to the dam's face as it sank. Each bounce reduced the bomb's forward velocity while maintaining its rotational energy. By the time it reached the target, it would be moving slowly enough to sink vertically, but with enough momentum to stick. Wallis presented his findings to the Ministry of Aircraft Production. They were skeptical but desperate. Every month, German factories produced more weapons. Something had to be done. In early 1943, the Air Ministry reluctantly approved further development under the code name Upkeep. Wallis had 8 weeks to turn his bathtub experiment into a functional weapon. He moved his team to the National Physical Laboratory and began scaling up. The bomb would weigh 250 pounds, shaped like a massive oil drum, and spin at 500 revolutions per minute before release. It would be dropped from exactly 60 feet at precisely 230 miles per hour, released at exactly 425 yards from the target. Any deviation, a few feet too high, a few seconds too early, and the bomb would either shatter on impact or skip over the dam entirely. Trials were conducted in secret at Reculver Bay on the Kent coast. Early tests were disastrous. Bombs shattered on impact. Others skipped wildly off course. Wallis returned to his calculations, adjusting the casing thickness, the spin rate, the release mechanism. He worked 18-hour days, testing prototypes, filming the results with high-speed cameras, measuring angles to the fraction of a degree. His colleagues marveled at his obsession with measurement. He would study a single frame of film for hours, noting how water pressure deformed the casing, how backspin affected trajectory. For Wallis, failure was not discouragement, but data. By late April 1943, Wallis had refined the design. The bomb worked, but only if dropped with perfect precision. The RAF formed a special squadron, 617 Squadron, under Wing Commander Guy Gibson to carry out the mission. The pilots trained relentlessly, flying Lancaster bombers at terrifyingly low altitudes over British reservoirs. They practiced at night, skimming just above the water, learning to judge distance by eye. To ensure they released at exactly 60 feet, engineers rigged spotlights beneath each aircraft, angled so that when the beams converged on the water, the altitude was correct. To measure the exact distance to the dam, a simple triangulation device was used, aligning the dam's towers through a homemade sight. It was improvisation married to precision. Wallis attended every test flight, standing in the cold at the edge of the reservoir, watching through binoculars as the Lancasters roared overhead. When a bomb bounced correctly, he noted the exact conditions. When it failed, he demanded to know why. The pilots, initially skeptical of this gray-haired civilian, came to respect his relentless focus. He wasn't asking them to die for a theory. He was proving test by test that the weapon would work. Live trials with explosive-filled bombs were conducted only 3 days before the raid. The first successful breach of a test dam confirmed what Wallis had calculated 2 years earlier in his garden. On the night of May 16, 1943, 19 Lancasters took off from RAF Scampton. Each carried a single upkeep bomb, spinning in its cradle beneath the fuselage. The crews, 133 men in total, flew at treetop level across occupied Europe, navigating by moonlight to avoid German radar. Wallis remained at Scampton, pacing the operations room, listening to crackling radio transmissions. He had done everything he could. The rest was mathematics and courage. At 12:28 a.m., the first wave reached the Möhne Dam. Gibson's aircraft made the initial run, releasing its bomb at exactly the calculated point. The cylinder bounced 3 times, struck the dam, and sank. 30 seconds later, a column of water erupted 1,000 feet into the air. The dam held. A second bomb was dropped, then a third. On the third strike, the massive wall cracked. Water burst through in a churning torrent, sweeping away everything in its path. The crews moved to the Eder Dam. 2 more bombs. The wall collapsed. Millions of gallons roared into the valley below, destroying power stations, factories, and infrastructure for miles. When the Lancasters returned to Scampton at dawn, 8 were missing. 53 aircrew were dead. But the mission had succeeded. Wallis, who had spent the night in silent agony, wept when he learned of the losses. He had given them a weapon, but he had also sent them into the fire. For him, the mathematics of destruction were inseparable from the mathematics of sacrifice. The cost was unbearable, yet the result was undeniable. 2 dams destroyed, German industrial production crippled, proof that precision, not brute force, could break the unbreakable. The bouncing bomb raid, Operation Chastise, became one of the most celebrated actions of the war. Newspapers hailed it as a triumph of British ingenuity. King George VI visited Scampton to congratulate the crews, but Wallis deflected the attention. He insisted the success belonged to the pilots who had flown at suicidal altitudes with unimaginable skill. When asked how he had conceived the weapon, he gave the same answer he always did: measurement, observation, repetition. The only way to solve a problem is to break it into smaller problems until each one becomes solvable. For Wallis, there was no mystery, only method. Yet the raid's immediate impact was only the beginning. The principles Wallis had discovered, precision delivery, rotational stability, underwater explosion, became the foundation for an entirely new class of weapons. He went on to design the Tall Boy and Grand Slam bombs, massive penetrating weapons that could destroy hardened bunkers and railway viaducts. Each was a refinement of the same philosophy: measure the target, calculate the forces, build the weapon to exact specifications. By 1945, Wallis's designs had destroyed more strategic targets than any other British engineer. After the war, Wallis continued working at Vickers, turning his attention to supersonic flight. He designed swing-wing aircraft capable of hypersonic speeds decades before the technology became standard. He developed earthquake bombs for deep penetration, prototypes for variable geometry wings, and theoretical studies on transonic aerodynamics. His notebooks from the 1950s contain ideas that would not be realized until the jet age. But Wallis himself remained focused on the same principles that had guided him since his youth. Every design began with a question. Every question demanded measurement. Every measurement led to refinement. In 1968, Wallis was knighted for his contributions to engineering. He accepted the honor with characteristic modesty, insisting that innovation was a collective effort. Those who knew him said the title changed nothing. He still arrived at the office early, still sketched designs by hand, still challenged younger engineers to prove their assumptions rather than trust their instincts. He disliked publicity and avoided interviews. When asked about the bouncing bomb, he would smile politely and redirect the conversation to the bravery of the air crews. For Wallis, the weapon had been a solution, not a legacy. Sir Barnes Wallis died in October 1979 at the age of 92. His funeral was attended by engineers, airmen, and scientists who had worked with him over 6 decades. A memorial service was held a year later at St. Paul's Cathedral, where the Archbishop praised him as a man who had turned imagination into mathematics and mathematics into history. Yet even then, Wallis's true legacy remained difficult to define. He had not built empires or commanded armies. He had simply solved problems that others declared unsolvable. The bouncing bomb, dismissed as madness by those who should have known better, had worked because Wallis refused to accept that impossibility was anything more than insufficient calculation. He had taken a child's game of skipping stones and transformed it into a weapon that changed the course of a war. But the weapon itself mattered less than the method. Wallis had proven that precision, discipline, and relentless measurement could overcome brute force and guesswork. That belief, more than any single invention, became his enduring gift to engineering. Today, the story of the Dambusters is taught in schools, dramatized in films, and remembered as one of the great feats of the Second World War. Yet the man who made it possible remains a quieter figure than the pilots who flew the mission. Wallis never sought that balance. He understood that history celebrates action, while the work of calculation remains invisible. But those who study his papers, now archived at the Science Museum in London, see something different. They see a mind that treated every problem as a series of measurable variables, every failure as data, every success as confirmation that the universe operates according to rules that can be understood. The dams of the Ruhr were rebuilt within months. The factories resumed production. The war continued. But something had shifted. The British had demonstrated that even the most fortified targets could be destroyed if the weapon was designed with sufficient precision. That knowledge, born in a garden washtub and perfected through exhaustive testing, became a turning point in military strategy. Precision bombing, guided munitions, and surgical strikes all trace their lineage back to Wallis's insistence that accuracy mattered more than payload. In the end, Barnes Wallis's legacy is not a single invention, but a way of thinking. He showed that the impossible is often simply the unmeasured, that every great leap forward begins with a simple question and ends with 1,000 careful observations. That genius is not inspiration, but discipline. The bouncing bomb worked not because of luck or intuition, but because Wallis had calculated every variable, tested every assumption, and refused to stop until the mathematics matched reality. That quiet determination, more than the explosions over the Ruhr, is what still echoes through the world of engineering today. The accountant who became a codebreaker, the turbine designer who powered an empire, and the aeronautical engineer who taught bombs to skip across water, all of them understood the same truth. Progress is not a moment of brilliance. It is the patient accumulation of measurements, each one bringing the impossible a fraction closer to real.